Welcome back to another installment of Stoichiometry with gas laws, and we're incorporating molarity as well. So in this one, we have 6.5 grams of aluminum reacts with 475 milliliters of a 1.75 molar hydrochloric acid. Now, the volume of this is of a molarity. This is an aqueous solution. And therefore we're not using gas laws for the 475 milliliters. People often just look at volume and go straight to gas laws. This one has molarity, and therefore we will use the equation for molarity, which is molarity equals to moles over liters. And then it says that hydrogen gas is formed, and we're going to want to know what volume of hydrogen gas can be formed. Now, before we get to that, we are given two certain amounts of two reactants, which means one of them will probably run out and one of them won't. If we're dealing with a titration reaction, they both run out and there's no excess. But this is not the case. It's not a titration. It doesn't say so. And we're looking for the volume of hydrogen gas. If the conditions are 0 degrees Celsius, and, not or, but and 100 kPa, we can use 22.7 equals to 1 mole as a conversion factor. Clearly, it is not those conditions. It's not 100 kPa. It's 98.4. It's not 0 degrees Celsius. And therefore, we're going to use PVnRT to solve for volume. So how do we go about doing this? If you look at the notes that I provided to you, we're going to go from one reactant, which is going to be grams of aluminum, to moles of aluminum, and this is going to be the first box, the second box. And then we're going to use coefficients to go to moles of hydrogen gas, but we're going to stop there. We're going to stop at this third box and drop out and then go through PVnRT if that's the answer. But we don't know if we're going to use up 6.5 grams of aluminum. So we have to start again with the other reactant. Now 475 milliliters is 0.475 liters. We're going to multiply that times 1.75 molar of hydrochloric acid to equal to moles of hydrochloric acid. And then we're going to go to moles of H2 gas. And we're going to compare these two, and whichever one is smaller is the maximum amount we can form, because whichever one is smaller, that's the one in which the reactant ran out and therefore limiting. So this A and B question, we have to solve A before B because we have to figure out which one is limiting and therefore which one is excess. And certainly to figure out how much of the excess is left over, we have to figure out which one's actually in excess. I've worked out these problems and I got 0.241 for the moles of hydrogen gas formed if we use up the aluminum, and I have 2.77 moles of hydrogen gas formed if we use up all the acid. Since the acid forms a larger amount, we can't make that. The point at which we make the smaller of the two, which is 0.241, means that reactant, which is aluminum, will run out. The maximum amount of hydrogen gas that aluminum can make is 0.241, and so it runs out, which means we cannot make the 0.27. This is our crap that we don't ever use anything. We don't use this number, and this is going to be our theoretical yield. However, we need to convert this into liters, and now we're going to start all over with a rearranged ideal gas law. The good part about these tutorials is you can stop them and go back and look, and like lecturing, it's kind of hard to put the pause button on me, but now you can do this and then go back. So far, what I've done in the top left in the red is I have copied the number of moles of the hydrochloric acid that we started off with, which is how much we have, which is going to be the 0.475 times 1.75. To answer B, we will need to calculate how much we used, and then we'll subtract it, and then we'll divide it by the original volume. We are assuming that these volumes do not change because most of this volume is water, and they really don't change much at all. If we're talking about 2 sets of aqueous solutions and we pour them together, we will assume the volumes will add. Because if you pour 50 in with 150, we assume it's 200. In the blue, I've set up my equation. I started off with the ideal gas law right here, and then I rearranged it. So I'm solving for what I want to solve for. I'm solving for volume. That's what dictates it. N is moles, which is what we have right here. This is the maximum amount of hydrogen gas it can form. T is temperature. It must be in Kelvin, so I added 273. It usually doesn't come in Kelvin because our thermometers don't really read in Kelvin. The pressure must be kilopascals. It doesn't matter the number, it must be kilopascals because we're going to use R as 8.31, and that's kilopascals, liters per mole Kelvin, which means when we solve for volume, it will come out in liters. So now what you got to do is plug and chug. When you plug it all in and solve for it, you get 6.27 liters of hydrogen. I have the unit of measurement, I have the chemical, and it is 3 sig figs. The temperature started off with 35, so you may think that's 2 sig figs, but we added, which means we round to the smallest place value that they all have in common. 273 and 35 means we round to the singles, which means we gained a sig fig. So we don't have 2 sig figs for temperature anymore, we have 3. So the answer to the maximum volume of hydrogen gas that can form is 6.27 liters. Now we have to calculate the amount of hydrochloric acid is used. We're going to start with the limiting reagent. We're going to start with the limiting reagent. This is what our notes say. If you want to figure out the amount of excess left over, you start with that, which is going to be aluminum. Aluminum runs out, and we're going to the excess reagent, but we're going to go to moles of HCl so we can subtract moles. You could go to molarity in this case because the volumes don't change, but as soon as we're adding volumes, it doesn't work. So it's easier just to go to moles. And the math says if used, and we are going to use all this up, then used. So this is how much of this we use, not have. So let's do that math. So I went from 6.5 grams to moles of acid, right? We're not going to molarity yet. We're going to moles of acid, and then we're going to subtract moles from moles. On the left side, this is how much we calculate we have. I just calculate how much we use, and then we subtract to figure out how much we have left over. And we have 0.18 moles left over. So I'm going to get 0.108, not 8 moles, and then I'm going to divide it by the total volume, which is the same 0.475 because that's it got to be in liters. And we get 0.23. You might have gotten 0.227, but honestly, since the molarity initially is only good to the 100th spot, then this will only be good to the 100th spot as well, but that's okay. So this is the molarity left over, which makes sense because we started off with 175 molar, nope, 1.75 molar, and we used a lot of it because the difference between how much we can make was small, which means we used up a good portion of it, and 0.23 compared to 1.75 is a good portion used up. So this makes a lot of sense. I hope this helped.